Yeah, so today I'll be talking about using document embeddings and recommendation systems. Yeah, the topic actually changed from what it was before and due to something out of my control, so sorry for that. Yeah, so basically, here are the topics I'm going to cover today. So there's actually a couple of kind of basic concepts that we need to cover before we can talk holistically about using document embeddings and recommender systems. So we'll give a brief intro to these concepts. And yeah, just as Aki mentioned, please feel free to interrupt with questions if you don't understand something or have like some kind of helpful comment. Yeah, so just a quick self-intro. So currently I'm a data science manager at Indeed. I'm working on recommendation systems. And previously I did analytics and machine learning roles at Google, Supercell, and Smart News, a Japanese news startup. And actually, most of my machine learning knowledge was self-taught via free content and events like the ones from Machine Learning Tokyo. So I'm actually like very grateful for this community and all the talks and content that is provided. And so I'm glad to be finally giving a presentation myself today. And I'm originally Taiwanese American, and I've lived in a couple of countries, including Finland, where Aki is from. Yeah. So diving into the actual topic, so what is the high-level idea? Like, why do we want to use document embeddings for recommendation, right? So we want to be able to generate high-quality recommendations by leveraging embedding vectors. So I'll be using the two words like embeddings or vectors kind of interchangeably in this presentation today. And these can be generated by deep neural networks. And also, if we're doing a retrieval task, we can use an approximate nearest neighbors similarity search algorithm to do that effectively. So I'll be covering this in a bit more detail. Yeah, so like why do we want to do this, right? So basically, we want to somehow extract the meaning. We want to extract the semantic representation from raw text, right? So we want to leverage more advanced NLP techniques. A lot of recommendation systems actually rely on dumb string matching, right? So like your query string has to match with the document, some string in the document for the search result to show up or for the recommendation to be shown. And, like we should try to be smarter than that, right? Also, we want to, there's a lot of manual feature engineering you could do to process the text, but it would be nice if, you could just let the neural network do that for you, right? And also, we want to be able to adapt to many languages, and there's several pre-trained models that help you easily generate embeddings in multiple languages, so that's also very nice. Yeah, so just to set up for the rest of the presentation, right? Here is kind of like a very typical recommendation system architecture, right? You have a client that could be, for example, the website, right? And there could be a request like, okay, given this user, find good items for this user, or given this movie and find similar movies or something, right? And you have a retrieval step where let's say you have like a database of 10 million or a billion items, right? And you want to kind of find let's say 10,000 items that might potentially be good, right? And then you have a ranking step, a ranking component after that, where you use like a more advanced machine learning model to score and sort those items, right? And then you return the top n items to the client. Yeah, so we can apply document embeddings to the retrieval, both the retrieval and the ranking components, as I'll explain later. Also, I'd like to introduce approximate nearest neighbors. So many of you might have heard of K nearest neighbors algorithm, right? Where basically given like a bunch of vectors or points, right? And given a query vector, you want to find the K nearest vectors to the given query vector, right? So with K and N, typically you would need to calculate the distance to each and every one of the other vectors, which is very time consuming, right? But with approximate nearest neighbors, we can actually like very quickly approximately find what the closest vectors are, right? So again, if the query vector represents a given movie and you're trying to find the similar movies to that movie, then you could just try to find the movie vectors that have the closest distance to your given query vector that represents the movie. Yeah, and with approximate nearest neighbors, you're sacrificing accuracy for speed, right? And there are like actually a lot of different algorithms and libraries for doing approximate nearest neighbors in different ways. Actually, just a couple of days ago, Google released this paper and library called SCAN. And basically they use this kind of like math trick with related to product quantization to achieve state-of-the-art results. So essentially you can sacrifice a little bit of accuracy for a lot of speed, for a big speed improvement, if you choose the right algorithm and tweak it right. Also introducing word embedding vectors. Basically, the original word-to-vec algorithm basically, turns each word into a vector, right? And this vector has some kind of semantic meaning, right? So the direction and the magnitude of each vector, which represents each word, has a meaning, right? So here you can see that queen minus king approximately equals woman minus man, right? So those where those arrows are in this embedding space is actually meaningful. Yeah, so also introducing, sorry, I'm just kind of like covering all the kind of like prerequisite topics to my presentation before I dive into the meat. Transformers is also like a very important concept for NLP and embeddings nowadays, right? So you might have heard of these famous models called BERT or GPT-2, GPT-3, and the transformers is the underlying kind of a neural network architecture component for these models, right? And this diagram that I'm showing now is just the encoder portion of the transformer architecture, and the BERT model is actually just a stack of these encoders. And transformers rely on this mechanism called self-attention, where each token, or basically each word, pays attention to all the other tokens, including itself. In this way, the embedding vector that is generated for that given token is dependent on the context, dependent on the words around it. Yeah, and so BERT is arguably the most famous, or I don't know, maybe GPT-3 is more famous now, but arguably the most famous transformer-based masked language model, right? So this stands for bidirectional encoder representations from transformers. So it's basically we're making like a vector representation of text using this transformer architecture. And so after this model was released, a lot of NLP benchmarks set new records using BERT, and it's trained in an unsupervised, or you could see it as a self-supervised way. One way is you can mask some tokens from the input text, and then you make the model attempt to predict those tokens that you masked. You can also try to predict the next sentence to train this model. Yeah, and as I mentioned, this is a stack of encoder components from transformers. And Google spent a lot of money to train this BERT model on a lot of text, so that you can use it for free, basically. And also, there's various organizations that made a version of BERT for other major languages, such as Japanese, French, German, etc. So it's very nice to to be able to use these for free. And BERT was originally 110 million parameters, which you might think is a lot, but I think GPT-3 now is like over 100 billion parameters. So yeah, they keep on getting bigger. So there's actually kind of different shortcomings of BERT, right? And they're related to this topic of document embeddings, which is the topic of this presentation, right? And using it in a production recommendation system, right? So often people complain that BERT is too slow. I would assume that GPT-3 is even slower, right? So what can you do about this? You can distill the model into a smaller model. So basically, you can have make a smaller model that kind of learns to emulate the behavior of the bigger model, right? And you can also kind of use some sort of system architecture that does like pre-calculation. So you're doing kind of the inferences and recommendation offline, and then saving those results rather than doing a forward pass through the model in real time. Another issue is that BERT is bad at long text sequences, but there's actually different transformer architectures which are faster than O of n squared time complexity and memory complexity. And actually, this is the topic of the bonus topic, which we'll talk about at the end if we have time. Also, someone argued that BERT is actually kind of doesn't represent a long text sequence, is not optimal for representing long text sequences. So there's the paper in the library that addresses this called Sentence BERT. And their library is called Sentence Transformers. So you can fine tune on a natural language inference dataset, for example, and then pool the tokens in a certain, the token vectors in a certain way, such that the text representation becomes more suited for generating good representations of longer text sequences and comparing them via cosine similarity, for example. Yeah, and then also BERT is good for general purpose text, because it was trained on general purpose text, right? But what if your use case is something special, like like medicine or finance, or I don't know, like theoretical physics or something? So you can actually do further pre-training of BERT or a similar model using text in your domain. Right, so I want to kind of explain this concept of further pre-training versus fine-tuning. Right, so given this BERT model that that Google already provided, like what else can you do with it after that, right? So with pre-training, that's kind of just doing more of what Google already did with the original BERT, except you provide, so it's self-supervised learning, but you can provide more raw text without labels, for example, from your domain, which might be medicine or finance or something. And then fine-tuning usually refers to supervised learning, right? So you provide some labels, such as something was clicked, like the recommended movie was clicked or it wasn't clicked, right? And then you backpropagate the loss from that if the label doesn't match with the prediction, right? So yeah, so pre-training BERT usually doesn't make sense because it's very expensive, right? So you can do this within domain further pre-training. And you can save this further pre-trained model for various downstream tasks, right? So you could, for your company or for your, I don't know, like medical association or whatever, right? For your domain, you can create a model using text from that domain and then, save it for various downstream tasks, right? And then so for specific tasks, you can do the fine-tuned supervised training, right? So, using, like, for example, the click logs from like what was recommended on your website. So yeah, this paper down at the bottom, how to fine-tune BERT for text classification, that talks about this topic more. Yeah, so when I say fine-tune, like how do you actually like set this up in terms of model architecture? So it's typically you just like slap on a single linear fully connected dense layer on top of the BERT model, right? And then you have some prediction loss after that, right? And then you just backpropagate through the whole model. And you can just connect that final layer to this one token in the final layer of BERT, which is the CLS token, which just means like short for classification. yeah, since this token is kind of paying attention to all the other tokens, then essentially like all the like information about this whole like input sentence or input document is captured in the vector for this one token. This is what a lot of people do. However, you can also like take the average across like all the tokens in the final layer instead of using that CLS token vector. So something you could do actually is, you know, just, and this relates to the idea of stand on the shoulders of giants, right? So all these cool organizations and companies, they spend all this money and effort to like make these awesome models for you. So you can just, you know, and they spend a lot of money on it, and you can just, you know, take that model off the shelf and do something cool with it, right? So Google trained BERT, and then Hugging Face company, they made Distill BERT, which is a distilled, smaller version of BERT, right? And then UKP Lab in Germany, they did some further fine tuning on this, of that model using the Stanford Natural Language Inference dataset, you know, which makes the representations more appropriate for document embeddings, right? And then you, at your company, you could take this and further fine tune this model for whatever you want to do at your company or organization, right? So just a little like quick demo. And by the way, is ever any questions? Everyone's still there?
Yeah, still here. There hasn't been any major questions, so
okay.
I think we can just go ahead and then move to discussion at that. Yeah.
Okay. Okay. Cool. So yeah, can everyone see my Jupyter screen here?
Yep, works well.
Yeah. Okay. So yeah, here you can see that it's very easy. So this sentence BERT or sentence transformers library, you can just import it like this. You can just download and load the pre-trained model. This is the name of the pre-trained model. You can just put it into this model variable here, and you can just encode, you can just generate like a vector from this sentence that I typed, right? And you can also, here I'm generating 4 vectors from these 4 sentences that I typed. So the first sentence, you know, machine learning Tokyo is awesome. Data science in Japan is very cool. The quick brown fox jumped over the log, and a fast rabbit leaped on top of a tree. So you can see that the first 2 sentences are semantically similar to each other, and then the third or fourth sentences are also similar to each other in meaning, right? So you can see that you know, if you calculate the cosine distance, which is just 1 minus the cosine similarity, you get like a, you know, small distance between the first and second sentence, but then you get like a larger distance between the first and third sentence because they're the meaning of them is quite different, right? So you know, so this is just, you can do this with a model that I just took off of the shelf, and it only took you know, 2 sentences to load this model. So that was, you know,
just a quick question.
Uh-huh.
Is this notebook, by the way, in GitHub or somewhere, or can you share it later just for reference?
Yeah. So the code is, the code is here. Sorry. So it's on this
okay, cool. Thanks.
Slide here. Yeah. And also I did this fun thing was I just I took like the like all these kind of machine learning related Twitter handles, right? And then I scraped their tweets, and then I created like an embedding vector for each of the tweets, and then I just took the average of the tweets for each. Sorry, the average of the embedding vectors for each person or for each Twitter handle, right? And then I kind of visualized it using TensorBoard. So this is like super easy to set up. And so here we have, so original vectors are in 768 dimension space, but this is projected to 3 dimensions, right? And using a PCA. And you can see that like if you search for, you know, Jerry, so that's me, you can see that, oh, I tweet similarly to Elon Musk, apparently. And yeah. Yeah, and let's see, we can try like MLT. Yes, MLT tweets similarly to, so you can see MLT here. tweet similarly to OpenAI. Then we can also check out Susanna. So Susanna seems to tweet similarly to Hardmaru, who is David Ha, the head of Google Brain in Tokyo. Although it might be because she's like retweeting what he says sometimes. Oh yeah, it's right here. Yeah, you can see Susanna and Hardmaru here. Oh, and Jan LeCun is nearby too. Nice. Okay. Anyway, so that was just like a little fun thing to show. Okay, so back to the deck. Go ahead.
Yeah, there was one question which I think is worth addressing. There was a question: BERT seems useful in research. Is it feasible to be used in production?
Oh yeah, definitely. So I think there are many companies using BERT in production already, but it depends on how you use it in production, right? And then I'll go over like some of the different ways to do that. But I would say that there are still many companies and organizations struggling to put it into production in the way that they want to. Yeah. So, yeah, but yeah. So I'm gonna talk about the productionization part. Okay, so so basically there are architectures that can incorporate BERT in different ways, right? So here where you see like query tower or doc tower or cross attention model, like you can think of that as the BERT part, or you can replace it with XLNet or some other transformer based model, right? But essentially here are different ways to incorporate it into your neural network architecture, right? And I think it's important to differentiate or to categorize the approximate nearest neighbors compatible architecture with those that are not compatible with approximate nearest neighbors. And I'll explain why in a bit. But basically you can see here that, let's say you're trying to predict movies that are given an input movie, like find other similar movies, right? So if you like create an embedding of the given movie and then create an embedding of all the candidate movies, and then at the end you just take the dot product of these two embeddings, or cosine distance, then this architecture is compatible with approximate nearest neighbors because you just trying to find the distance between these two vectors. And you can also use a Siamese network approach to this, which just means that the parameters on the left tower are equal to the parameters on the right side. And that can speed up the training. Okay, and then on the right, we can see these architectures that are not NN compatible, right? So here, right, we might be feeding in, let's say it's again like the embeddings based on, let's say the descriptions of two movies, right? So you can feed just everything in concatenated at the very beginning, and then do a forward pass through this neural network. And so this allows for kind of more interaction between the features of the two embeddings. However, so you get the benefits of that, of allowing more complex interaction, but you lose the ability to compare the first movie with the second movie just by a simple dot product or cosine similarity calculation, right? And therefore it's not compatible with approximate nearest neighbors. Yeah. So to kind of recap, there's a trade-off when you're kind of deciding between which category of architecture you want to use, right? So if you want to use something that's NN compatible, then your speed is very fast, right? Because you don't need to calculate the distance for each and every candidate item, right? Whereas if it's NN non-compatible, then that means you have to calculate, you have to do a forward pass for each candidate item. So it's the fastest it can be is O of n, where n is the number of items. So therefore, you know, since if it's ANN compatible, then it's good for large scale retrieval, right? If you're, you know, trying to search across a billion items, then you would not want to kind of score each of those billion items, right? And however, if you're trying to do ranking, then it is probably better to use an ANN non-compatible neural architecture because you can capture, as I mentioned, the more complex interactions between, let's say, the first movie and the second movie, between the two items you're trying to compare. And then so for the model quality or the recommendation quality, the ANN non-compatible one is going to be better, although you can still probably get like a decent model quality, even if you're restricting yourself to an ANN compatible architecture. Yeah, also in terms of loss functions, you know, when you're training your model, like triplet hinge loss is one good option. So for example, like let's say you're trying to recommend items for a given user, right? So you can use the embedding of the user, right? So it could be, let's say, embedding the text written by the user, like it could be a movie review text or something, right? Then let's say you have like positive labeled items, right? So maybe it's like movies that the user clicked on, or movies that the user you know, gave like 5 stars on or something, right? So you treat that as a positive item, and then you find also negative items, right? Like maybe stuff that items that the user didn't click on. And then you kind of put these 3 things, the user, the positive item, and the negative item, into one triplet. And then you just, you know, you set up your loss function such that the model tries to make the positive item closer to the user and make the negative item further away from the item. Sorry, yes, the negative item further away from the user. And so this kind of like creates an embedding space where the model is able to kind of differentiate between the positive and negative items, which is what you want in like many kind of ranking tasks. Okay, so here I'm going to go through some options of like how can you actually incorporate these document embeddings into your production system, right? You know, so let's say you have like an existing retrieval system, right? Which is, let's say it's like a, you know, dumb like string matching kind of retrieval system, right? So you could actually set up like another retrieval system, which is based on the embeddings and the approximate nearest neighbor search, right? And you could, you know, combine the results from the existing and the new system, and then your downstream ranking component can just you know, sort and score all of these things, right? That's one way you could do it. Another way is you just you replace your existing retrieval component with the approximate nearest neighbor search. That's option 1. Option 2, and I think this is more practical in many cases. So you replace your existing retrieval component with the approximate nearest neighbor search, but you also combine this with some rule-based filters, right? Or kind of these like this Boolean logic, right? So for example, like maybe let's say if you're recommending movies, right? And let's say the I don't know, like the user like clearly stated that, okay, they don't want like you know, like adult rated films, or they don't want like horror films, right? And you want to make sure there's like a 0% probability that they're going to be shown adult content, right? So you don't want to rely on your ANN search to implement that kind of rule, because you know that the ANN search is kind of a soft, fuzzy thing. You can't really, or it's quite difficult to implement hard rules in that kind of system, right? So you can have like a rule-based heuristic system that is combined with your embedding search, and this is possible. So, for example, in using the ANN plugin in Elasticsearch, you know, which is like a scalable version of Lucene. So option 3, you know, you could replace your existing ranking model right? And so in this case, you don't need to use approximate nearest neighbors search anymore, right? So you have more flexibility in the type of architecture that you use. You know, or option 4, you could actually provide embeddings as features that feed into the ranking model, right? Because you might also have other features that are not embeddings, right? So in addition to the text that you're feeding in, you might also have categorical features, right? Like, you know, like is the user on you know, iOS or Android, you know, that would be like a binary categorical feature, right? So, you know, you might want to, you know, use more features than just the embedding vector. Yeah, so an example of this option 4 is actually included in this library that was just released by LinkedIn very like 2 weeks ago or something. And you can see that, so like where it says text encoding, right? It's using like some model, like such as BERT, or you can use a convolutional neural network or long short-term memory or something, right? And you can create embedding vectors. And then later down in the architecture, this is combined with other features such as dense wide features and sparse wide features. Yeah, and at the end, this all like you can concatenate them, and then, you know, add another like fully connected layer, and then finally connect that to the loss function at the end. And then you could, you know, backpropagate that loss throughout the whole network, or, you know, if that's too expensive, you could, you know, maybe freeze some of the lower layers, and then, you know, just update the weights of the later layers. Here's another an example from Facebook, which uses option 2 and 4, right? So remember, just a reminder, option 2 is you do retrieval using these rule-based Boolean filters in addition to this approximate nearest neighbor search amongst your embedding vectors. Right? And option 4 is, you know, feeding the embeddings as features into your ranking model, right? So this is actually yeah, including using embeddings both in the retrieval stage and in the ranking stage. So this is actually like a very cool paper, which I highly recommend. Yeah, you know, also for just productionizing your the calculation of these embedding vectors and also generating the recommendations. The actual, if you're, it depends on what kind of architecture you're using. But basically, you know, if you have a lot of data, right? So if you have, let's say, you know, like billions of items that you want to search across, and you might potentially recommend, right? You probably want to, you know, break this problem up, right? So, you know, you could schedule like a daily job or hourly job or whatever on Apache Airflow, which is like a really good workflow orchestration tool. And if you're using AWS Batch, you know, then you can have kind of each task as a Docker container, and you could kind of spin up, you know, like one Docker container for each batch of files, right? So like, let's say if you have thousands of files that contain your billions of items, or it could be a database, right? Then you could have like a separate AWS Batch job for each of those files, or maybe 10 files each, right? And you can just like send all these jobs to AWS Batch, and it will kind of dynamically auto scale and you know, just process the jobs as fast as it can without you know, overwhelming the server resources, right? So you basically, it's serverless, and you don't need to manage any servers. Yeah, so it's basically infinitely scalable, and it's also modular because each task is its own Docker image, right? So you could have like a task which is you know, pre-process the text data, and then another task which is you know, generate the embeddings from that text. And then another task which is, you know, generate the recommendations given those embeddings. So, however, this pipeline architecture wouldn't work well for real-time embedding generation. So, and also you have to like read and write to cloud storage after each step. So there's a bit of kind of network cost for that. And then you're also launching mini Docker containers. So there's a bit of overhead for those Docker containers. But I still feel like for a kind of non-real-time use case, for non-real-time calculation, I think this is like a good way to approach it. And you can also like pre-calculate the recommendations offline, and then kind of put the recommendations into like a real-time system like Redis or DynamoDB or something. And then, you know, serve those recommendations in real time, even though those recommendations were calculated offline. Of course, like whether or not you're able to do that depends on your given situation. But anyway, it's just one way to approach it. Yeah, so I've provided just some links to papers and resources here. So, you know, a lot of, you know, most of this is very recent. So I think it's like a very exciting field of research, but it's not just research. Like most of these papers actually talk about, you know, their actual experience putting this stuff into production in, you know, for like a real service or product. So I think it's really cool that, you know, you can, you know, be using these like really advanced models in production. Okay, so I'm done with the main topic. I also have a bonus topic, which goes kind of into the math of faster transformers. So as mentioned, so transformers are you know, the main component of these awesome models such as BERT and GPT-3, right? But they have time and memory complexity of O of n squared. So, you know, where n is the length of the sequence, right? So that's actually a problem because, you know, like if let's say you're trying to, you know, process like a book or just like a long article or something, you know, that becomes, you know, computationally prohibitively expensive when you try to process that, right? And, you know, this is like a bit painful for myself when I was, you know, training BERT on a V100 NVIDIA GPU with 16 gigabytes of memory. So each input example had about 1,500 tokens, or like kind of three, since I was using triplet loss, it was like 3 groups of 500 tokens. And I could only use a batch size of 3. So I was only able to process like 4,500 tokens at once. And so I really wish it could, you know, process a lot more at a time so I could speed it up. Even then it was 100 times faster than processing on my MacBook, but yeah, still too slow. Okay, so what can we do about this, right? And actually, so there's like a bunch of research, you know, very recent that tries to address this, right? And I think it's very promising, right? So the first line there, recurrent, that just refers to like the typical recurrent neural networks, right? Where your complexity per layer is O of n. And again, n is like the length of the sequence, right? And then the transformer paper, which was released in 2017, right? That's O of n squared. That's the normal transformer that's used by most of these models like BERT. Yeah, and then, you know, we get faster and faster, like, you know, O of n root n, O of n log n, and then there's a bunch of like O of n algorithms that came out. So most recently, Big Bird from Google, which came out a few days ago. Yeah, so again, you know, the reason we have this O of n squared is because each token is paying attention to all the other tokens, right? So in this image, we're just drawing the lines for the word it, but actually we need to draw these lines for each and every of these tokens, right? So if you have, you know, 10 words, then you have about like 100 of these connections. Yeah, so to go a little bit deeper into reviewing what this attention mechanism is doing, right? So you have this query, right? So it's the representation of the word or token that's used to kind of match with the other tokens. Sorry, my daughter is making a bit of noise. And then the key vectors are kind of like, you know, here it's pictured as like a folder, but it's what's used to match the query with the other words. And then the value is actual representations of the words. Essentially, we're just like multiplying these three things together, right? So we're essentially just taking a softmax of the query vector times the key vector, and then at the end multiplying by the value vector, right? And it's actually like a matrix because we're doing this in a batch. Yeah, so yeah, basically what happened is that in around 2016, everyone was like, oh, like recurrent neural networks and long short-term memory, they're so cool, like all the best NLP is done with these things. And then around 2018, everyone's like, oh, like, RNNs were so, like yesterday, like now, like BERT and the transformer models are cool now, but that might not be the best way to think about things. So there's this interesting paper called Transformers Are Actually RNNs. And it's basically just using a math trick to speed up the attention from O of n squared to O of n, right? So if you look at the just the typical attention equation, right? Again, you're just multiplying kind of the query, taking the dot product of the query vector and the key vector. You can actually just generalize that to be like a similarity function, right? So you're kind of taking the similarity between the query vector and the key vector, right? And then since you're calculating like a similarity, we can take like a lesson from the world of SVM support vector machines, right? Which uses this kernel trick. So you basically transform the vector, the query vector and the key vector in a way that if you take the dot product of those transformations, then you get the similarity function that you wanted, right? And if you kind of do this, then you can actually factor out the query vector from the summation, right? Which means that you can just calculate this summation for all the key vectors once, right? Instead of for every query, right? So this essentially changes the attention calculation from O of n squared to O of n. So it's basically a math trick. And furthermore, this paper actually does like one more thing, right? Which is, if we, instead of using this bidirectional processing as a BERT does, right? So bidirectional just means like for a given word, we can look both to the left of the word and we can look to the right of the word. Whereas if it's unidirectional, then you can only, for a given token, you cannot look at tokens to the right. You can only look at tokens to the left. Then we can actually reformulate this transformer as a recurrent neural network. This actually has like a really big, this leads to a very big speed up in the calculation, because you can just store the key times value matrix as a state and then just update it in each step. So yeah, this is just graph showing that the line at the bottom is so this is just kind of graphing the complexity versus the sequence length, like the number of words that are being processed. And you can see that the line at the bottom is what's achieved by the authors here, right? So it's like an order of magnitude faster. And then another paper that came out by Facebook AI, they actually take a totally different approach, right? And all these names are confusing because this is called linear transformer, this one's called linformer. There's also other stuff called like reformer and longformer. It's, everything ends in former, I guess. So here what they're doing is they're doing like, it's another math trick. So they're just from kind of linear algebra and the kind of like dimensionality reduction techniques. You like what people try to do often is you take like a matrix and you try to project it into a lower dimensional space, right? So they kind of do this proof that you can take the V vectors or matrix in the case of using a batch, right? You can take the value matrix, you can take the key matrix, and then you can project it into you know, a low dimensional space of just k dimensions, right? And so the chart on the left shows that you know, you can make the inference time way faster, right? If you just compress this matrix into like fewer dimensions, right? And they're showing that you actually don't lose that much information when you do this compression, right? So it's kind of analogous to the concept of PCA, principal components analysis, where you know, you just take the couple of dimension. If you're given a matrix, right, you just take like the couple of columns that are the most important, or you take the couple of you can represent the information of that matrix with just a few columns. And most recently, and this is again, I think like 1 or 2 weeks ago that this came out. So the Big Bird paper. So there's this rule in the world of like transformers research where like your model like has to be named after a Sesame Street character, like otherwise you're not cool. And yeah, I think there's even like I think Baidu or someone like released a model called Ernie. Anyway, so yeah, Sesame Street is like a children's show in the US, I think. So, but what this is doing is it kind of doesn't make every token pay attention to every single other token, right? So each diagram is basically for each row is the token position that's paying the attention, and then each column position is the token to which attention is being paid, right? So in a traditional transformer architecture, this square would be completely full, right? Because everything is paying attention to everything, right? But that's very computationally expensive, right? So you kind of just pay attention to a part of the tokens. And so, you know, you can, and there's like different ways to like choose just like a portion of the tokens to pay attention to, right? So you can do it randomly. You can do like window attention, which is, for example, for each token, you only pay attention to itself and the tokens like immediately to the left and right, right? And then the global attention just means like, okay, you can always pay attention to like the CLS token, the kind of sentence start marker token. And in this way, you can actually, and you can kind of compensate for this kind of sparser attention by adding more transformer layers, right? And since we have global attention, each token is guaranteed to be connected to each other token across, if you're looking across 2 layers, right? Because, you know, everything is connected to the global attention tokens, and then the global attention is tokens are connected to everything else, right? So across 2 layers, then everything is connected to everything else. Yeah, but it's still like O of n, not O of n squared for a given layer. Yeah, so anyway, the conclusion is there's several ways to make transformer-based models faster. So like all these people who are saying, oh, we can't use BERT or we can't use a transformer-based model because it's too slow. Like hopefully in the near future, they can stop saying that. But it's still like a very new area of research, right? A lot of what I talked about today, you know, just literally came out like a few weeks ago or like this year. So, but I think there's a lot of excitement in the community around this research. And also like these older concepts like RNNs, you know, we shouldn't, or like LSTMs, we shouldn't forget about them just because they're not trendy. I mean, neural networks themselves, they were like really not trendy for a long time. And then we later on found out that they're actually really cool. So just, you know, don't only pay attention to the things that are trendy. Yeah, yeah, no pun intended, by the way. So yeah, that's
overall a good thing, I think, in a lot of machine learning things and other fields as well. Like there's some things which are trendy, but like the basics kind of work still.
Yeah. So yeah, a lot of these like old concepts are actually like really useful for a reason. Yeah, and so here's some links related to what I just talked about, and I especially highly recommend this YouTuber called Yannick Kilcher, who explains these papers like much better than me and much better than the paper authors. So yeah, highly recommended. He's also part of the group that does the podcast called Machine Learning Street Talk, which I think is a great podcast. Anyway, yeah, that's it from me today.